welcome back. Next, we'll design a down counter. In the last video, we designed an up counter, and the reverse of up counter is a down counter. So it basically is a counter that counts from some larger number to a smaller number. So a down counter is a counter that counts from a higher number to some lower number. Fine. And let's design a down counter. So let's design a down counter that counts from say decimal 7 to 0, and then again it will reset back to 7. That's understood, but this time around again let's make a twist here that additionally the counter must set an LED on if it holds say an even count. Fine. Let's try to design. Again, starting from the first step, we have to capture the finite state machine, the most important step. So the first part is pretty simple. You will have a set of states, like you will have the starting state as 7 because it is a down counter. Then we move to 6, 5, 4, 3, 2, 1, and the last state will be 0, and then it will reset back to 7. Then again, there is no external input, so whatever the transitions are, they will be governed by the clock only. Fine, something like this: 6 to 5, 5 to 4. Every time the positive edge comes, positive edge of the clock comes, these transitions will happen. And then as usual, we'll have some initial state, which in this case will be state 7. But an additional thing is that every time you have an even count, your circuit should glow an LED. Now 7 is an odd number. So if I say choose an arbitrary output, let's say X. Now 7 is an odd number. So in this case, X will be 0, depicting that the LED will not glow. 6 is an even count. So here X will be 1 in the sense that an LED will has to glow, because this is basically the uh, schematic. Yeah, this is basically the graph description of your circuit. From here on, we will build up, design the circuit. So we have to include these information, whatever information is in your design, it has to be included in the state machine. Similarly, for 5, LED will not glow, that is X will be 0. For 4, X is equivalent to 1. 3, X is equivalent to 0. 2, X is equivalent to 1. 1, X is equivalent to 0. And let's assume 0 is also even. Yeah, because 0 is neither even nor odd, so let's consider it as odd and put X is equivalent to 0. So when your circuit, when your state machine is in the state 2, 4, 6, it should output a 1. And when it is in the rest of the state is 0, 1, 3, 5, 7, it should output a 0. So this will be my finite state machine. Next, I will create a standard architecture. Again, in this case, it is pretty straightforward. The combinational logic, which we have to resolve. So this will be the combinational block. And the sequential, the memory part of it, it is already resolved because there are 8 states, so we will need a 3-bit state register. Which means there will be 3 state outputs: S2, S1, S0. Fine. And so we'll also have This will be N0 N1 N2. Fine. Now let's name them S2, S1, S0, N0, N1, N2. Now the additional thing in this circuit is I also have an external output X for the LED part. Baki, this is the combinational logic. So this is the standard architecture. Once we're done with the standard architecture, next step is we have to encode the state. Again, in this case, it will be pretty straightforward. We just have to, replace the state name with its binary equivalent. So I will have states 7, 6, 5, 4, 3, 2, 1, 0. So we'll replace them by their binary codes 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, and finally 0, 0, 0. As far as transitions go, there will be direct transitions every time a clock happens. I will have an initial state and then I will have an output 0. For the even count, it will be 1. Fine. So this will be the encode state. And from here on, I will create my state table. Now, in this case, I only have 3 inputs, the state inputs, but I do have 2 kinds of outputs, the state outputs and also the external output. So we'll again create same way, we'll create the state table. Wherein inputs on one side, outputs on the other side. As far as inputs go, I will only have the state inputs S2, S1, S0. As far as outputs go, I will have the next states N2, N1, N0, and the output X. And for every input combination, we have to find out what the next state will be and what my output will be. So if I start from the initial state 1, 1, 1, from here on my next state is going to be 1, 1, 0. And since this is an odd count, X will be 0. Then 1, 1, 0, the next state. From here on, I will move to 1, 0, 1. Now, since this is an even count, so output will be 1. Fine. Similarly, you will fill it up. So next one will be 1, 0, 1. From here on, I will move to 1, 0, 0, and X will be 0. From 1, 0, 0, I will move to 0, 1, 1. Output is 1. From 0, 1, 1, I will move to 0, 1, 0. Output 0. This output will be determined by these inputs. So currently it is holding 3. 3 is odd, so output is 0. From 0, 1, 0, I will move to 0, 0, 1. Now since 0, 1, 0 is 2, so 1. Likewise 0, 0, 1, I will move to 0, 0, 0. And for the last state, I will have 0, 0, 0. Next state will be 1, 1, 1. And output will be again 0. Fine. So this is my state table. And again, from this table, I will get some set of equations for N1. Yeah, let's start with N2. If I express in terms of min terms, it will be, now we have to look at the other order. See, this is basically min term 0, min term 1, and this is min term 7. Accordingly, you have to adjust. So it has min term 0, then I think it has 1, 2, 3, 4, 5, 6, 7. Likewise, N1 has min term, it has 0, then there is 3, 4, and 7. N0 has min term 0, 2, 4, 6. We also have X, which has min terms 0, 1, 2, 4, and 6. Right? Then if you wish, you can simplify them. So in this case, it will be pretty simple because you will be only requiring a 3-variable K-map. And using that 3-variable K-map, you can actually simplify it. So that is comparatively simpler. Like I will have a map like this with S2 complement S1 complement S2 complement S1. Fine. So let's say we solve it for, let's say for X. So you have 0, 1, 2, 3, 4, 5, 6. So now combination like this. Then you can form two combinations out of this. One will be this, and the other one will be this. Likewise, you can simplify it. I've already simplified it because this is something which is from the first chapter, and you will have N2 in the simplified form S2 S1 plus S2 S0 plus S2 complement S1 complement S0 complement. Then N1 would be S1 S0 plus S1 complement S0 complement. Similarly for N0 we'll have S0 complement, and X will be S1 S0 complement plus S2 S0 complement. And all you have to do is implement these equations and adjust them in this standard architecture like we did for the up counter. Fine. I will leave that as an assignment. I mean, you have the equations here, just adjust them in the computational part. So this is yet another counter, the up count, the down counter. The important thing is here is that apart from this main counting process, you can actually also involve the inputs and the outputs to add additional functionality to your circuits. Like with the down counter in the last video, we included an external input B, which actually controlled the transition from one state to next state. So every time B was high, then on the next positive clock edge, we were able to change states. And in the down counter, I included an external output which, based on the count of the circuit, would actually control an external LED. Right? So these kind of small additions we can always bring into our designs. So I'll stop here.